So thank you, Pietro, for this amazing introduction. I feel a bit embarrassed. And yeah, my talk will, it's really looking back and looking a bit forward, depending also how much time we want to spend on that, on the Higgs boson. So I'm from CMS, so I'm a bit biased, so don't get upset if maybe there are more plots from CMS and from ATLAS, but I will try to cover both the results. Yeah, so it will be about the Higgs boson and the Higgs field. And as you all know, the Higgs boson is a prediction of a mechanism that took place at the very beginning, at the early universe, less than a picosecond after the Big Bang. The Higgs field filled the universe, filled the space uniformly, and the elementary particle interacting with it gets mass. In this way, I just tried to move your faces. I wanted to see some. Okay, I see at least one face. So in this way, both the W and Z boson acquire mass while the photon remain massless. And this leads to the electromagnetic and the weak interaction to become distinct in their action. And the Higgs boson is really, it has a really amazing impact, and the universe is looking like we know it today because of the Higgs field, because the fact that, for example, the electron become massive allows the atom to form, and this endows our universe with the observed complexity. The Higgs field, the Higgs boson is a very special particle, and it's the only elementary particle with spin 0 that we have discovered and observed up to now. And okay, it has a 0 electric charge, and it's even under parity and charge conjugation that can really well understood by the fact that the mass cannot depend on the reference frame. So it was a very long road to the discovery of the Higgs boson. And from the theoretical and experimental point of view, we can maybe start 70 years ago with the Young and Mills theories for the interaction between particles and gauge field. Then there was the basic idea from Glashow that was essentially saying that the weak and electromagnet interaction could be of the same kind, but with a very different propagator. So one very massive propagator, the other massless propagator. And then in 1964, there was Braut, Engler, and Higgs with the Higgs what we call the Higgs mechanism, or whatever you want to call it, because there is always discussion about it. And all in 1967, 1968, Glashow, Weinberg, and Salam formulated the standard model as essentially we know it today. So putting together the three ideas that I mentioned before. And in 1970, Toft and Veltman demonstrate that the standard model is indeed renormalizable, also with the addition of the Higgs mechanism. And from the experimental point of view, these years were very productive, because in the 1973, the charm quark was discovered, and it was essentially at the same time predicted by the GIM mechanism, the GIM mechanism. Gargamel, the same year, discovered the weak neutral current, so observe, let's say, in an indirect way, the Z0. In 1975, there was the tau lepton. In 1976, the beauty quark. And then in 1983, the UA1 and UA2 discovered the W and the Z. And then at that point, there was essentially the need of trying to measure as precise as possible all these quantities, so the W, the Z, the sinus theta Weinberg, and understand if the family were 3 or more. And then LEP was approved, and in parallel ERA at DAISY, and this 10 or more year really signed the triumph of the standard model with all the precision measurement from the experiment at LEP and ERA. In parallel, at Tevatron, there was the top quark discovery in 1995, and then we will come to the 2012 with the LHC and the Higgs boson that I will talk more today. So just to go back a little bit, because as Pietro said, I worked for more of 10 years at LEP. So LEP, as you know, was the accelerator before LHC. So at the time, in 83, as I said before, after the discovery of the W and the Z, the LEP was approved. So they began the excavation of the tunnel of the 27-kilometer circumference ring, 100 meters below ground. And in 89, it was, I think it was the beginning of August in 89, there was the very first interaction at 91 GeV. So electron and positron collided in, well, I must say, in 3 out of 4 of the experiment, and only after a few days they managed to make them collide in the 4 experiment. LEP took data from 89 to 2000, and the first 6 years, it took data at 91 GeV, so around the Z0. And the last 5 years, well, 5 years and a half, it took data at increasing energy up to 209 GeV. The experiment at the time were thought to be huge, but we were not so many. We were 500 people per experiment. And we didn't produce about more than 350 papers per experiment. So what I also want to underline that is very hard now to remember how little we knew about electroweak physics and also QCD before LEP started. QCD was really at the beginning at the time, but also electroweak physics. We just discovered the W and the Z. And LEP did indeed a gigantic leap and allow us and really measure with very good precision the number of fermion families and with per mil or better precision all the electroweak quantity, the standard model quantities. But it was also important what we did not discover, because it allowed to, with the exclusion of many beyond the standard models, we could really essentially confine the space and say where to look better for new physics. The Higgs boson was searched since the beginning, both at LEP1 and at LEP2. At the end of the LEP, these are the final results. So LEP with the 4 LEP4 experiment together combined could set a limit at 114.4 GeV. So we could exclude an Higgs if lighter than that. We would have expected to exclude the Higgs boson at 115 GeV, but there was a slight excess in 2 of the experiments, so the observed limit was a little smaller. As you see from the curve, from the CLS curve, the limit is very solid because the curve is very steep. So it was quite precise results. So it was an electron-positron machine. So it was the perfect machine to search for the Higgs, but only if the Higgs was lighter than the center of mass energy minus the Z mass. And unfortunately, the center of mass energy was limited to 200 well, in principle was 200 GeV. At the end, we managed to go up to 209 GeV by playing various tricks and by really pushing to the extreme all we could push. And then we reached the 115 GeV. In reality, in 95, at the research board in June 95, we were proposed to buy more superconducting radio frequency cavity for 32 mega Swiss franc in order to reach 220 GeV of center of mass energy. That would have allowed us to find the Higgs if it would have been lighter than 129 GeV. But unfortunately, this was not, CERN decided not to go higher than 200 GeV and then to let the space for LHC. And so that was it. We really pushed a lot, but we didn't manage. Yeah, just one historical sentence when in 2000 we really made a real battle with the CERN management to keep going with LEP. Ting was saying something that is a Nobel Prize because it's a Nobel Prize for the discovery of the J psi, so the charm quark, said we should continue LEP because at LEP every event is signal, while at LHC every event is background. And indeed at LEP the event, I don't have the slide is hidden. But at LEP, essentially, what you produce is just one Z and one X in case you are producing the X. So you have really only two objects. So you don't have background. So anyway, so they decided to stop and they started really to dismantle already at the end of 2000. Here is are two pictures at the beginning of 2002, where the tunnel that was the LEP tunnel and the new LHC tunnel is completely empty. So they empty everything. And here, this hole is really a hole from the CMS cavern when they dig the 100 meter to go down and they finally reach the LEP tunnel. They make a hole to enter in the tunnel from the ceiling. Okay, so as you know, we had the first interaction in 2009 and the first run in 7 and 8 TeV center of mass energy from 2010 to 2012. I also want to stress that, okay, I will talk about analysis. I will not talk about any other things, but it was an amazing work of an enormous number of people to construct, install both the experiment, the accelerator, to design the trigger, the data acquisition, to design the grid, to deal with all this amount of data, and also, of course, simulation and reconstruction and everything. But also there was, as Pietro was saying, there was an enormous work from the theoretical community. And I just want to mention a bit, since it's a bit of an historical talk, I want to remind how the LHC cross-section working group was born. It was in 2008, the Giampiero Passarino had the idea of the group for the first time, underlining the urgency, because he said that discovery can come at any time, much sooner than we expect. And indeed, we agree between the two of us and to start this group. And only then in August 2009, we met at the cafeteria with some people from ATLAS. So Bill Murray, Nisati, and Kuyan were from ATLAS. And in November in 2009, we met in Torino, theoretical community and experimental from ATLAS and CMS, and it was by chance that it was the exact day that LHC delivered the very first proton-proton interaction. So we agree on a program and what to do, how to organize ourselves, And then indeed, we asked the permission from the experiment. And in January, the experiment let us go on and formally recognize it. And just 1 year later, we had the first yellow report. So essentially, since day zero, the Higgs analysis from ATLAS and CMS have been using the prescription from the working group. So at the very beginning, these were the results. So we had these are plots and table from the first yellow report of the group. So you see cross section for some of the production mode. So the production mode we were studying at the time. We were plotting them as a function of the Higgs mass up to 1 TeV. Branching ratio were known a few percent level, some a little bit better, but mostly few percent level. And, oh no, sorry, these were the cross-section, sorry. These are still the cross-section running from few percent to 20% for the gluon-gluon fusion. And the branching ratio were essentially computed by using two codes, HDK and prophecy for F. And these were the precision, again, at the level of 1 and 2%. Then what happened? So as I said, we started to take data at 7 TeV in 2010. And already in September 2010, we had a spectacular event in CMS. We observed 4 muon, very high PT, as you see from the table. And they were both coming from a Z, so the combination really was giving 2Z, decay into 4 muon. And it was really a spectacular event, very clean, that gave us a lot of excitement and, let's say, good omen for the future. In 2011, the situation became somehow very excited because these were the data, the plot of the invariant mass of the 4 lepton for CMS, then from 100 to 600 GeV. So these were the data we were observing. So we were having 2 interesting events at 120 GeV. 140 GeV, so the red peak. And we were completely excited about these 2 events. So CMS went into panic mode because he said, we must be sure what we are doing. We cannot go to the APS conference and showing this plot. Everybody think that we had discovered the Higgs. And then indeed, we had a huge help by theoretical community, in particular by the author of POWEG, that really help us in understanding all the background and ZZ channel for this particular channel. And so finally, we got the approval from CMS to present this plot at the conference, and ATLAS, on the other side, came exactly or somehow with a very, very similar plot, and with also one event around 140 GeV. So we were absolutely excited by that, but of course, it was too little to claim anything. And that indeed we kept taking data and analyzing them. And in December 2011, the 2 spokespersons presented the results of the Higgs at CERN, at a seminar at CERN. And the very important result essentially was that the 2 experiments could exclude the Higgs boson for very large masses, so from masses between larger than about 130 GeV, as you see from the 2 plots. And both of them were presenting an excess at low masses in between 115 and 130 GeV. As you see, both ATLAS and CMS had a free sigma excess at 125 GeV. So at that moment, we decided not to look at the data anymore, to blind the analysis, to work on our analysis and to optimize them for this region, so between 115 and 130 GeV, and not to look at the data essentially until LHC would have delivered a luminosity that it was sufficient for us to eventually discover with a 5 sigma significance a particle at 100, a Higgs boson-like particle at 125 GeV. And that was it. So essentially, yeah, maybe I skipped this slide, otherwise it takes a little bit of time. So that was it. We went, we were for CMS, we were the 14th of June. We had collected enough luminosity that would have been for the 125 GeV eventual Higgs boson. The analysis was ready. We froze it, and we decided we could open the box and look at the data. So we unblind, we run our program, and we projected on the screen. So here is what we could see on the screen that evening of the 14th of June. The photo is really miserable because we were forbidden to take photos. The photo was taken even if it was because it was not allowed, but we took it anyway, and you could see the peak at an excess, a very clear excess of data at 125 GeV. So here is then a plot that a better plot where you don't see the Z0, but you see just the intermediate part. And then you can clearly see the excess of event that corresponded to a Higgs of 100 coherent with the production of a Higgs boson at 126 GeV. The next day, then, we meet with the gamma-gamma people, so with the rest of CMS. As you understand immediately, as I spoke, that I'm in the HZZ analysis. So we meet with the other people of CMS, and also the gamma-gamma channel were observing a similar excess at exactly the same mass, at 125 GeV. So in parallel, of course, a similar situation was in ATLAS. The spokesperson agreed with the DG of CERN to present the results on the 4th of July. And so the 4th of July came. Just maybe a bit 2 words about this. Well, as you can imagine, this was an amazing moment because to see that you are indeed for observing a new particle was really amazing. Was really, I think the biggest professional emotion of my life. And personally, I couldn't sleep for days because I was too excited. And something that was very difficult after the 15th of June was to keep the secret because it was, we were not supposed to say anything, especially to ATLAS, because of course you wanted the results to be completely independent and unbiased. And so what was really difficult was to go around CERN, hide, and essentially not smile because of what we had observed. So finally, the 4th of July come. People knew because, of course, there was rumors of this seminar with important results. So many people went to sleep in front of the auditorium in order to be able to enter in the auditorium. So you see the people sleeping, the camping in front of the auditorium. The Higgs convener, one of the Higgs conveners from ATLAS sleeping, him as well on the floor. Then the people queuing already at 7 o'clock in the morning. And then, when after the announcement, you see all the director of CERN are completely excited about the discovery in the auditorium. And of course, the DG had invited also Engler and Higgs, and this is a picture of them sitting together and maybe speaking between each other for the first time after many years. So this was the situation of the 4th of July. ATLAS and CMS were observing an excessive event at 125 GeV in the 4-lepton channel and in the 2-photon channel. ATLAS was having an excess of about 6 sigma for all the channel combined. CMS was having exactly 5 sigma. And the average value of the mass was 125 GeV. The next year, not that year already in October 2012, but the Nobel Committee decided that they had to wait 1 more year to be sure that the reanalysis of the full run 1 was confirming the discovery. So only the year after, in October, the Nobel Prize was awarded to François Englert and Peter Higgs. The year after was also a very exciting year because we had a second big breakthrough. And essentially, we realized, thanks to the work of Kauer, Passarino on the production of off-shell Higgs, and Kaula and Melnikov, who put together these two formulas of the cross-section for on-shell Higgs and off-shell Higgs, that we could extract the width of the Higgs from the ratio of the on-shell and off-shell production, and we could extract the width with a precision of MeV, while the experimental resolution would have not allowed us to measure the width of the Higgs with a resolution better of the GeV, of the order of the GeV. So these are the very first results for the extraction of the width of the Higgs using off-shell production. And the first results allow us to set a limit on the Higgs width by 13 MeV. Well, we were expecting a bit more. This is something that is still valid now. So somehow we have a deficit of event in the off-shell region. So this was the really a second breakthrough that allowed us to reach a precision we could have never imagined. And then then run 1 stopped, and we were moving toward run 2 with very big difficulties in front of us, because the pile-up essentially was supposed to increase from 11 interaction per collision, per bunch-bunch collision, like you see now for what we were expecting in run 1, up to about 40 collision per 40 primary vertices per collision in the run 2. In the meantime, also the Higgs cross-section working group keep working, and essentially we were working to produce cross-section and branching ratio for the new energies, so for 13 TeV. And we keep adding new production mode, like the BBH or the single top H production. But at this time, essentially, we split let's say, the standard model Higgs, and we concentrated only on few GeV, around 125 GeV, and all the BSM possible production in case a heavy Higgs would have been produced. That was so the cross-section were anyway produced up to 1 TeV. The cross-section were also, then we started also to do this plot that was the cross-section as a function of the energy, in order to show that indeed the top Higgs was becoming 4 times larger than in run 2 with respect to run 1, and then we had good then possibility to also observe this final state. And this is a summary, essentially, of the theoretical calculation and this enormous effort of the theoretical community, to provide a precise prediction for all the production mode. So quark-quark, gluon-gluon X, you see the final theoretical prediction. I don't know if it's really the very final one, but it is. It's at N free LO and N free LL, compared with the ATLAS and CMS results. The fiducial cross-section computed as well at the same perturbative order. Vector boson fusion, where you see the uncertainties is almost undistinguishable by the dot. And in parallel also the PDF had an enormous effort to understand the discrepancies between the various groups and to converge with the precision of the order of the 2 to 3%. If from getting data from the run-2 at higher energy, so with higher cross-section and then increasing both, increasing thus the luminosity, you see that by moving from run 1 and run 2, we manage essentially to observe, or even with more than 3 sigma, all the production mode and the main decay mode. And also we started then to measure cross-section, fiducial cross-section, differential cross-section, and we are essentially having quite good precision that can go from 5% to 10% precision. So I want to present you the latest results from the mass that we have now, so the measurement of the X mass. So the X mass is measured from the gamma-gamma and 4-lepton decay channels. The mass is the most important parameter for an elementary particle, and when the mass is known, all the other properties are precisely defined in the standard model. The two channels have very different systematic uncertainties because essentially different detectors contribute to the measurements. And you can see here the old results from run 1, that was a 240 MeV. And then you see the latest CMS results from the 4-lepton channel only, with a 0.12 GeV precision, and the ATLAS results that is combining 4-lepton and gamma-gamma, and it's the most precise results up to now, that is 110 MeV. And these two results were presented recently at LHCP in Boston. So you see we have a per mil precision. Hopefully we will also get the 2 gamma results from CMS, should be coming soon, and hopefully the combination of the two experiments. For the width also, there was a huge work done by the two experiments, and with the run 2, we are reaching the few MeV. So we are reaching a measurement, it's a 3 sigma measurement, where, well, it's not really 3 sigma, but 3 sigma is essentially the observation at 3 sigma of the off-shell production. So we are observing indeed that the X is produced off-shell, and these are the value of the width extracted by the method, by this method of off-shell, of the ratio between off-shell and on-shell production. Well, there are many results about the spin and CP properties. I don't show them here. They are very complex analyses. They are going on. There are many different studies. Essentially, the spin 0 and positive parity are at more than 99.9 confidence level. And we are now studying the possibility to have a combination of CP odd and CP even contribution, but essentially the study now are excluding CP odd coupling for the moment. This is run 2 results. Okay, the usual channel that we knew already, so gamma gamma, ZZ, tau tau, BB bar, but also two new ones that are essentially rare channel. One is the decay into Z gamma that both ATLAS and CMS observe at 2 sigma. I forgot to update this plot with a combination by ATLAS and CMS that observe at the Z gamma decay at more than 3 sigma, and then the mu mu X decay into mu mu at 3 sigma by CMS. So while the coupling of the X with the third generation is well established, the coupling with the second generation is a work that is going now, and it's possible thanks to all the new methods. So these essentially are advanced machine learning and deep neural network method that manage to improve substantially efficiency and purity, and allow us to observe the decay into X into muons. Here there are two nice events where the X is produced in vector boson scattering and in association with two top. And as you see, for the moment, we observe with a 3 sigma significance. The charm analysis is also very complex, and also again, thanks to the machine learning, we managed to have access to this channel. The most important background in this case is the X decaying into BB bar. So here there is really, the machine learning are dedicated to distinguish the charm from the B. And here there are the results from ATLAS and CMS. And well, at least one nice positive result is that we could observe the Z decaying into CC bar at Hadron Collider. You tell me when I have to stop, Pietro, because I didn't check much the time.
It's 45.
Okay, I will present still the coupling, and then maybe I conclude, and then we can see if there are questions we can discuss about the future, a possible future.
Okay, thank you very much.
So precise what we are interested now is essentially measure the various coupling and the various vertices, so all the X coupling with the fermion and boson. So we can combine all essentially all the production mode and decay, and combine in a total cross section in order to compare with the standard model prediction. And here there are the results from ATLAS and CMS from run 2, where you see that there is a very good agreement with the standard model with a few % precision. And you see from run 1 to run 2, we more than half the precision, so double the precision, sorry. And also you see the theoretical work has been impressive because it's almost double as well. Here are essentially the results from ATLAS and CMS. Well, here are the CMS results for the production mode on the left and decay mode on the right. All at 5 standard deviation, a part of the Z gamma and the single top. ATLAS as well, ATLAS presents the results in terms of cross-section instead of ratios of cross-section. We are working with the differential distribution, so going double differential, single differential, and this is important in order to also understand the QCD effect. So as a function of the number of jet at low PT, etc. And as I said, what we are really trying to investigate are the singular vertex of the X with the vector boson or the fermion. So this is the old framework, the kappa framework that we are still using because it's very somehow easy to use. and it's okay to use it if there is agreement between data and theory. These are the results for the Kappa framework. So you see, again, good agreement with the prediction between with the standard model in ATLAS and in CMS with very good precision of the order of 3 to 10%. And essentially, these are some results that show how we improve in these 10 years, thanks to the statistic, not only the statistic, because we had indeed 30 times more Higgs events in run 2, but also to the ingenuity of the analyzers, because essentially all these machine learning and due analysis method allow us to go from run 1, where you see this red circle, to run 2 with the black one. And by extrapolating to the end of LHC, we can see that we will reach between 2 to 5 let's say 1 to 5% precision for the different individual coupling. These are I think the two very beautiful plots that show the coupling as a function of the particle mass, where the lines are is not a fit, but it's a standard model prediction. And you see indeed that the data agree with the standard model over many order of magnitude in the two axes, so in particle mass and in couplings. So we found the Higgs, we measured the mass, so we understood the minimum of the potential. What we are trying to do now is to study the double Higgs production, and that because this will allow us to understand the curvature of the potential. The curvature is very important because it allows us to understand if our universe is stable or not, and how it could eventually evolve. So if we look at the top quark mass versus the Higgs mass, the value that we are measuring now, it seems that our data point to a region of meta-stability. That means that the minimum of the potential is not the real minimum, but there is indeed a new minimum where our universe could fluctuate and could evolve for tunneling effect. So it's very important to measure the curvature of the potential. It's a very difficult measurement because the cross-section is very small. It's 10 to the minus 3, the single Higgs production. And to access the lambda, so the parameter of the potential, we could access it with a double Higgs production that you see is the green vertex of the first and the third. But when we have double Higgs production, of course, we are penalized by the fact that this diagram are interfering negatively, and of course have to on top of this, you have to extract one of the two diagrams from the other ones. We have the first results on double H production. So the CMS is an old plot. The ATLAS is the new plot from LHCP. So we keep adding channels, and we are improving the method to essentially work with multi-Bs and multi-tau, so to increase the efficiency. And for the moment, we have a cross-section that is still 2-3 times from the standard model one. So we hope that, we are quite sure that we will observe at 5-6 standard deviation the double Higgs production at high luminosity LHC, but we still also hope to get better than 50% uncertainty on the kappa lambda by the end of high lumi LHC. One interesting result, and the the VVHH vertex has been somehow observed to be different from 0. Okay, we are also using single Higgs production to help us extracting lambda, but of course the results for the moment are interesting, but are not helping so much the double Higgs production. And maybe, yeah, I can close here, and then eventually we come back. So we will keep working. So we hope to have a 50% to observe double Higgs production, to have a 50% measurement on kappa lambda, and we will measure between 1 and few percent the various coupling. So I skip all the EFT. I guess you know much more than me all about the EFT stories. So what we really want to do now? So we really want to measure with enough precision all the properties to verify the standard model. And of course, this is a very important goal, but this is also has a second effect, that is essentially that the studying the Higgs with very high precision allow us to understand if there is new physics and how the universe will evolve, and also it will have also important effect on cosmology. So in these last 10 or well now 12 years, experiments have done much better than expected because we understood very well our detector and we improved a lot in our analysis technique. Theoretical prediction have understood a precision that we could have never imagined, at least the theoretical community would have not even dreamed at the time they started 15 years ago. The group, the LHC Higgs cross-section working group has been really a game changer, to use the expression from Fabiola. And we are now really in a precision era for what concern LHC. And this is important per se, but also because it allows us to understand if there is new physics. So by the end of the LHC, ILUMI LHC, we will have 180 million Higgs per experiment. That is essentially, that means that up to now, we have only analyzed 3% of the total number of Higgs boson that we will have by the end of LHC. And so it means that it's a very interesting, many interesting years are waiting for us. And I stop here.